Thank you all for having me here, and thank you for the warm introduction, Saeed. So today, as Saeed mentioned, the webinar will be about automated surveying using AI on Google Maps API satellite imagery. My name is Akash Vidyadharan. I'm the Chief Technology Officer of Infralytics. And just a quick introduction about myself. I have a background in aerospace and computer systems engineering from Iowa State University. And I've been the CTO of Infralytics for the past 5 years, where we built projects and products specifically related to geospatial, AI, as well as drone-related work. So for today's webinar, we'll be talking briefly about Infralytics and our traction. Just a quick overview of artificial intelligence, machine learning, and deep learning with its definitions and few use cases. Different data collection methods that have been considered and used by our team and their pros and cons. And finally, a live demo as well as introduction to the satellite data AI case study. So brief about Infralytics. We are a company that makes data meaningful. We specialize in engineering-based data analytics and development of custom software products. We primarily focus on proprietary machine learning, AI development, and automation. And we work with multispectral data processing, including HD images, 3D, thermography, LiDAR, and telemetry. And the data that have been collected from various sources, including satellite, drones, aircraft, vehicles, telescopes, text, and database. We've also had wide experience in developing apps on Android, iOS, and the web. Overall, we have collected, analyzed, and visualized data for clients in different fields. Just some traction recognitions by Infralytics so far. We received the UAE AI seal and were audited by the UAE Ministry of AI. We were a part of the DFA Dubai Municipality Future of Construction Challenge. We were also selected by the US National Geospatial Intelligence Agency for their Geospatial Accelerator. And we're also a member of the Catalyst Space Accelerator, which is part of US Air Force Research Lab and sponsored by Microsoft. We're also part of the Black & Veatch Ignite X Startup Accelerator program. And we have successfully executed multiple projects for regional and Fortune 500 companies. So now let's delve into AI, ML, and deep learning definitions. So some interesting facts about AI. It can be applicable to any data type and is applicable to any field of study, no matter which field you're in, whether it's engineering, insurance, energy, defense. It's highly multidisciplinary in nature. So just to show you, how does AI help? What are the actual use cases of computer vision? Well, here you can see one of the examples from drone data where a user actually captured multiple drone images of buildings and its surrounding infrastructure and needs to identify defects. Usually this job would be done by an engineer where he would look through multiple images, inspect it, and create a PDF report. But in this case, the machine learning itself was trained using prior images to identify different defect types, including water ponding, exposed rubber on the edges of the roof, steps which do not have contrasting paint, as well as cracks on roads and walkways. Similarly, another example that we'll talk about in more detail for today's webinar is the object and attribution detection from satellite imagery. And over here, you can see the machine learning, instead of the human going in manually, it identified rivers, ponds, transmission towers, as well as different types of rivers. So some definitions in practical terms. So what is AI? It is the capability to imitate intelligent human behavior using machines and algorithms as long as we train them. And machine learning and deep learning are specific focuses of the field of AI. And this could very well be the next revolution in business technology. So in terms of machine learning, it is the creation of algorithms to solve a particular problem. In mathematics and computer science, it essentially means creation of a very precise sequence of algorithms to do specific actions. So in a simplified manner, we can say that it is a recipe for putting together ingredients to produce a certain output. What is deep learning? So this is a subset of machine learning where it's not just a set of algorithms, but multiple layers or numerous layers of different algorithms working together in a synchronized manner. Each of these would provide a different interpretation of the data, And for this webinar, we'll be referring to whatever we do as machine learning. So a simplified explanation of the machine learning process. The first step would be manually labeling and identifying the object of interest, which in this case is the blue dot. So in this case, a subject matter expert or a human would just go in and start drawing labels or annotations around the object of interest from multiple different data, from multiple different images. Then the machine learning algorithm would be built and it would be used to train all this annotated data. Now, what would the output be after this? Once the training optimization is done, the machine learning algorithm will then be able to automatically identify all the blue dots or the object of interest in this case, even if there is a certain amount of variability in the environment or the areas of interest. And over here you can see this. So what does the AI workflow process look like? The first step is data collection using sensors mounted on drones, satellites, vehicles, or any other platform, because you do need the raw data for training. The second step is the data analytics and the creation of algorithms for the identification of objects, anomalies, and its accurate count and attributes by training the algorithm. And finally, once all the processing once all the processing is complete, it will be the data visualization step, where it'll have a software with proprietary tool to visualize the different types of data which has been analyzed by the algorithm. In this case, we will only be using satellite data sources for our case study. So what does the machine learning lifecycle look like? In general, it is a continuous learning process in which the first step we'll have to ask ourselves is, what is the problem and how are we solving it? The second step would be to collect, organize, and clean the data in order to get the most ideal data set. Once you get the best data set, you would then train the algorithm for the first round of training, and then you would test it with untrained data sets to make sure your algorithm is performing and its accuracy is as expected. Once this is done, you would collect feedback from the subject matter expert, retrain, and optimize the algorithm to perfect the accuracy and improve the results. So when to use machine learning? Usually when there is too much data to handle, when the process that is being done is highly repetitive in nature, and when there is consistency and quality improvement needed. And in terms of business cases, over here, it would help reduce cost and free up staff to be much more productive. So what would the journey your organization may need to take for a machine learning program implementation? The first step would be to collaborate with field subject matter experts to make sure that you understand the definitions and the objects or anomalies of interest that you're trying to define properly. The next step would be to define a short-term and long-term vision along with a problem statement to solve. The third step would be to formulate detailed requirements and features, including architecting a solution that may be multidisciplinary in nature. The next step would be to apply the cost-benefit analysis of the existing process that is being done manually versus a proposed AI. If there is a cost benefit, then certainly it is worth investing and building the AI algorithm. And the last step is to develop working prototypes for the solution and to compare its accuracy with the human. Now let's talk a little bit more about the data collection methods. Just so that you know, there's multiple different ways data can be collected for surveying, starting with satellite data, where there's a lot of open data available, especially by the UAE Space Agency, aircraft and helicopters for a much more close-up view of the area of surveying, drones when the area of surveying is relatively smaller and a high level of accuracy is needed. And we also have vehicles, embedded sensors on infrastructure, handheld cameras, as well as any kind of existing database. So why choose satellite data analytics? The main purpose is the scale that satellite can cover. It virtually has global coverage, and it also has a high resolution of 50 centimeter per pixel, which is quite high, where you can identify most of the major features such as buildings or water bodies or vegetation or roads with rather high level of accuracy. And in the field of, in the space agencies, new satellites are being launched with high resolution on a very frequent basis. And there are also multiple satellite data vendors that are available in the market with vast amounts of open data that can be used for training. So just to show you an example, on the left side, we have a drone imagery that was rendered of a particular building in UAE. And on the right side, we have satellite imagery. So just by this example, you can see that most objects are identifiable in both the images, and satellites are a cheap, fast, large scale, and consistent way of collecting data over drones. Now let's talk about the practical case study that we've built using AI algorithms. This was automated surveying using artificial intelligence and Google Maps satellite imagery. So what was the business use case here? It was for automated engineering survey for one of our clients. In this case, the client needed to plan the locations of wind turbines installation by identifying the types of buildings, types of water bodies, the types of roads, conditions, and its attributes, as well as trees and vegetation. And their existing process was to go through Google Maps data and to manually identify these objects and draw polygons around them by looking through the data, which was very time consuming. In fact, just for roughly 400 square kilometers, it used to take them nearly 2 weeks of manual work. On the next page, you can see our machine learning algorithm results, where it already identified all the structures, roads, water, and vegetation automatically. And it also identified object attributes. So for example, for roads, it was able to identify the length, the road type, the road condition, as well as the name of the road from Google Maps API. And all of this was packaged into a highly interactive web-based platform where machine learning runs could be requested at the click of a button, and all the data could be exported as GIS formats, mainly in KML, KMZ, and shape files. So here's just some additional sample output where you can see that the mean average precision was quite high. In fact, it was 92% for the identification of all the objects and attributes, as you can see here. Over here, you can see the trees, the water bodies, different types of structures such as residential and industrial buildings. And moving forward, you can also see here's just a sample of the machine learning run on a particular location where all the different types of roads are identified and color coded. And just to show you close up of just the detail and accuracy the machine learning algorithm was able to get, you can see it identified the gravel and asphalt roads and drew a midline for these roads. Similarly, in these two cases as well, over here it identified gravel and chip seal road, which is a different road type. Now here we shall see how the machine learning algorithm runs in real time on the front end platform. And we also have a demo that will go on during the Q&A session. So here you can see within a few seconds, the machine learning algorithm downloaded the images and has also started drawing the gravel roads and the midlines between these. Moving forward, you'll see that it also started identifying the receptors such as the trees, structures, and any water bodies that are present in the nearby area. Now, in terms of the type of imagery that can be processed from satellite data, it's not just 2D data or HD image data. It is also possible to extract 3D digital elevation maps from Google Maps API. The API has elevation for multiple points on a surface, on the surface of the Earth. And as you can see in this example, we were able to compile all of these points and render a highly accurate 3D digital elevation model from the data. So now you may have some questions. So how is the data uploaded? What is the speed of processing and so on? So in terms of processing, it takes around 1 hour on AWS cloud to process roughly 100,000 acres or 400 square kilometers of imagery. The ML process can also be made faster by utilizing larger servers on AWS, particularly with more GPUs. And satellite data was requested via Google Maps API directly to our AWS cloud. And over here, it was sent for the machine learning processing. So thank you all for attending the webinar. Now I shall actually show you a short demo of the 3D model as well as the live machine learning data. So for the machine learning, over here, you can see a particular location that was selected. And if you'd like to identify all the roads or receptors, it's as simple as clicking Start Machine Learning, selecting the roads, and clicking Go. And now in a few seconds, you'll see that the ML status will be changed to pending. The server will turn on AWS, and it'll start running the machine learning algorithm. Similarly, while this data is running, I will go to a different location and start rendering the 3D model. So this is an area at the Grand Canyon. So you'll see lots of slopes and crevices right here. And right now, the app is downloading all the elevation points from Google Maps, and it's rendering it in real time. So in a few seconds to a minute, we should be able to see a 3D model come up of the elevation model. So here you can see the elevation model of this particular area with the mountains and the plains right here. And as you can see, this was created by importing different points, creating a mesh of it, and then applying the elevation color scheme for the contours. Now let's go back to the machine learning algorithm. And as you can see, the machine learning is already in progress. And if I zoom in, you can see it has already started drawing the roads in this particular location. And this will keep going for the next couple of minutes. With that being said, as the machine learning is running, I'd like to entertain any questions or comments or thoughts on the webinar and any questions that you or your team may have. Thank you.
Okay, so thank you so much for your fruitful and constructive presentation. Now we will leave the floor to our audience to ask questions and start the discussions.
Thank you.
So there is one question from Iman. What software did you use for creating the machine learning algorithm?
Good question. So we primarily relied on two engines. So one of them is OpenCV for the computer vision parts, and TensorFlow was used for training. And in terms of the programming language, we used Python for the algorithm.
Okay. Here I have some few questions, Mr. Akash. So in general, what is the difference between the AI, machine learning, and deep learning?
Yeah, so in general, AI is more or less a broad field. It consists of many subparts of machine learning. For example, you have natural language processing, computer vision, machine learning. It's just the large, broad overview of the field itself. Now, machine learning in general is some place where you have to train an algorithm using data. And once you train this algorithm using data, it will start mimicking that process. So this is really what the broad definition is of machine learning and AI. In our use case, we're particularly using machine learning because we actually had to train the RCNN algorithm right here in order to mimic exactly what the human drew. So the first step was that we actually had some engineers draw roads for a few locations on this application itself, and then used this data for training. And now you can see the machine learning is drawing roads and midlines by itself.
Mm-hmm. Okay. Mr. Akash, in your opinion, how will AI impact the development of these applications?
So in most of the applications that we built, the case studies that I showed you from drone data and this satellite imagery as well, I'd say around 70 to 75% of the components were AI related, where to a point where all the automation that was done on complex data, whether it was 3D LiDAR data or HD images, AI played a huge role in it. In terms of business use cases, we have testimonials from many of our clients in different fields, whether it was insurance or engineering, clearly telling us that after they've implemented the AI algorithms, they have saved around 70 to 80% of the time of their current or of their manual existing processes, and they've used it in production ever since we built it for them.
Okay, fine. Here also one question from engineer Mona. She said, why you are drawing a midline?
Yeah, good question. So in general, our client, they requested this. The way that they were doing their surveying back then when people were drawing it manually was their engineers used to just draw a midline for the road. So they never created a polygon, because creating a polygon by a human takes a lot more time. But as you know, for machine learning, you can see it's drawing it just in a couple of seconds or minutes. Also, in the midline itself, when we export it into KML or KMZ, they wanted all the attributes to be written in a specific tabular format in this data. So this is the reason why we have the midline for each road. We don't have this for any other features, like for the trees or the houses. There is no midline. It's just for the roads.
Okay, and there is a following question from Mona also. She said, what if we have sand on the road? So which is a common in the United Arab Emirates. So is the algorithm robust enough to detect the road?
So in terms of sand covering up the road completely, we've, since this was built and tested in US environment, we didn't have much issues with this. One place where we did find a shortcoming in the algorithm was, let's say if there was very dense tree cover on the road where, trees entirely covered up this road and you couldn't see through it. In that case, the algorithm would just stop where the road, where the tree cover starts, and would only continue after, the tree cover was, after the tree cover was finished. So in terms of sand, you can see, it's actually detecting sand roads itself. So this is just the gravel road. So you can see it detects asphalt, concrete, chip seal, gravel, and dirt road. So sand in general has not been a problem for us, but trees have.
Okay, there's one question also by Shamim. What kind of output we will get from 3D model?
So there's multiple different outputs we can expect from 3D model. In terms of just the format of the data, we can get OBJ format, we can get LAS and LAZ format, which is point cloud format. So it's just many points arranged in an order. In terms of mesh, we can get MTL and GLB format. So the mesh format is what you're seeing here, where it merges all the points and you get this 3D GLB format.
Okay. Engineer Mina here, she is asking about if there is any trial version of the API.
You mean for Google Maps API, Mina, or? Okay.
Yeah, I think so.
Oh, okay. So for Google Maps API, I'll just load it quickly and I'll show you how it works. So the good news about Google Maps API is they have $200 worth of credits for free for anyone to use. And if your usage of $200 per month is, you go beyond $200 a month of usage, only then you have to start paying per API call. So you can see right here. And they also have many free requests where, especially if you're using some particular type. For example, static maps is what we use here. It's free if you use it on a mobile application. And for 1,000 requests, which is roughly 1,000 blocks of images from Google Maps, it's only $2. So you can see it's really cheap. And they also give you a big chunk of data for free.
Okay. Okay, Mr. Akash, there is one question also from Muhammad. He said, one issue when developing a deep learning model is the generalizability of the model. So what points should be taken into account to increase the generalizability of the model?
Yeah, it's a good question here because when we were training this algorithm too, if I, zoom out, let's just go to the, let me just load the map of US. Yeah, so here you can just see from the West Coast to the East Coast, there's different terrain. You have grassland, you have mountain, you have desert, you have farmland, and you have dense vegetation. The best way to take care of this generalization problem is to have a very diverse data set where you have enough data labeled or annotated on different types of locations or different environments. Um, in general, if you're looking for objects which are very discrete or very clear, like roads or houses which look similar in most places, this should affect the model less, just the diversity of the environment. But in case you're going from very different or just highly different environments, like from completely snowy area to a desert, this is where you need to have some level of diversity, where you do have some annotated data in the desert. You also have some amount of annotated data in the snowy regions. So just diversity of data should help you solve the generalization problem.
Okay, also Iman Swedi is asking, can you elaborate more on the attribute detection? So how did you train the model to read these attributes?
So yeah, I'll show you an example of just the different types of attributes that we're detecting. So while this location runs, let me open up another location. Okay, so here you can see, when I right click on a particular road, it tells me that the road is gravel, which is an unpaved road, and then the name of the road. And let's say let me hide and when I right click on this, it also gives me the length of the road. So in general, the attributes that we had to detect for this particular project was not so intense because, once we know the road type, which was detected by the RCNN algorithm, we could easily derive that gravel is an unpaved road. And in order to identify the name of the road, Google Maps API actually has the road name. So all we had to do was request the road name from the API and tag it to this particular line or this polygon. And the length was just measured by a backend tool. So I can just show you right here. If you click on any 2 points, you get the length. We just automated that based on the beginning and the end point of the line and got the results. So the attributes were not really trained. Most of these attributes could be derived once ML identified the few key features for these roads.
Okay, I have two last questions, Mr. Akash. As you know that deep learning deep learning network is a huge neural network with many hidden layers. So how to configure the number of the hidden layers and nodes within the neural network?
So this is rather difficult to answer, but a simple answer to this question would be you need to tune each parameter and run it on a certain test set to see which once you tune the thresholds to a certain number, you have to compare which ones give you the best results. That's the only realistic way to do it. More recent methods are there where you have unsupervised learning where the algorithm itself should do the testing, tune the parameters itself, and give you the best output. But this is still, I believe, somewhat of an open research topic. It's not commercial in nature yet, to a point where a company like ours can use existing libraries or research papers to build an app around it. So for now, we're still stuck. Data scientists are still stuck in a bit of a manual loop.
Okay. Just the last question. So Akash, as you know that the data pre-processing is an integral step in machine learning as the quality of the data and the useful information that can be actually derived from it directly affect the ability of our model to learn. Therefore, it is extremely important that we actually pre-process our data before feeding it into the model. So can you please elaborate about the data the data pre-processing? What are the filter, or what are the attributes? How to select the attributes, and so on?
Sure. So in this particular example, pre-processing was not a huge step, because really once the data was labeled, we just had to overlay the polygons on top of the image chunks. The only pre-processing that we had to do here was, I'll try to zoom in and let's see if we can see it or not. I'm not sure if you guys can, or if the audience can see it, but there's a thin white line right here where my mouse is.
Yeah, we can see.
Okay, perfect. So yeah, so this thin line basically is how Google Maps divides their images. So when we see the whole world as a map, Google Maps actually breaks it into many tiles. And these tiles is one API call, which we can download and use for, training or testing or running machine learning on. In our use cases, we needed a bit larger, we had to get larger tiles. So we had to get a set of tiles together. Now, why did we have to get a set of tiles zoomed out? This is because we wanted the machine learning algorithm to learn the context of the imagery. So not just the object of interest, like the road in one tile, but also how would the road look when it's zoomed out, a level or two outward. So this was the main post-processing that we had to do before training. But now after training is where actually a huge number of post-processing had to be done. So for example, you can see the generation of the midline was one of the post-processing steps. The second step was actually merging multiple polygons to make it a smooth road as much as possible. Because if you can see, there's vertical and horizontal line. And when the machine learning runs on smaller image chunks, it'll get one road as this length, the second road as this length, third road, it would be a very broken road. So what we had to do was we created a dilation algorithm, which would, really expand or make the road thicker to a point where it could catch or overlap with the road from the next image. And then it would, make the thickness of the road lower again. And this way you can see now we have a smooth road running down the entire length without any breaks or issues. And this was actually a major step because when the human draws, he clicks on many points and he just keeps scrolling through it. But the algorithm unfortunately sees the imagery differently and gets the images as smaller pieces. So the smoothing, the merging, and dilation were the bigger post-processing steps that had to be done by our team in order to, get the best results.
Right, clear. Yeah, so I think we came to the end of this webinar. Thank you so much, Mr. Akash, for this fruitful session. And thank you all for your kind interest in attending this webinar, and looking forward to meet you in our upcoming events. Thank you.
Thank you. Bye.
Okay, bye.